In the previous examples, we saw that we were able to compute the first few natural frequencies of these bars, and we were able to see that we could use principal coordinates to analyze the motion of the different nodes in the bar. But how do we know that the solutions we were getting were any good? In both of the examples, I chose an arbitrary number of elements and nodes to use to do the analysis. But how many should I have chosen to make sure I'm getting the correct solution? Well, in the first example where we had actually the analytic solution, we can directly compare and see when are we using enough elements because we know what the answer is. But in the second case, the tapered bar, we did not have the analytic solution at our disposal to directly quantitatively compare the results from the FEA to the analytic solution. And really, if we can get an analytic solution, there's not necessarily a good reason we want to then use an FEA anyway. But typically what's going to happen if we have well-behaved linear systems, which is the focus of what we look at in this course, the solutions we obtain should converge to a single value. So the idea we're going to use to do convergence testing is we are going to keep rerunning our simulation, and every time we're going to use more and more elements, which means we're going to use more and more nodes. And what is this going to do? It is partitioning our system into a higher and higher dimensional multi-degree of freedom system every time we rerun it. And what we can do is compare every time we use a finer and finer mesh, every time we use more and more elements, how do our natural frequencies values change with the increase in the number of elements or the number of nodes. And visually would be one way we could look at it is when does that difference in the estimate of our natural frequencies start to get small and basically stop changing as we keep adding elements. And when this occurs, then we have said that our solution has converged. Now, we want to note that just because it converges to a single value, that does not mean it is the correct value. We could have made a mistake in the modeling, we could have made a parameter error at some point, and we still have convergence. So we still need to consider, is the value it converged to a reasonable value? Again, we might not know what the solution is, but we can at least maybe bound it in some way, or we want to make some sort of inference. Is this a reasonable value that we should be obtaining? Now, as we add more and more degrees of freedom by making this finer mesh, we are going to be calculating more and more natural frequencies. So if we split it into n nodes, we're going to get about n natural frequencies. Because of applying boundary conditions and we reduce the number of actual degrees of freedom, it won't be exactly n. But just because we can calculate n natural frequencies, that doesn't mean that n of them are correct or even converged. What we're going to see happen is that the convergence is going to always go from the lowest natural frequency to the highest. So that means that if we are tracking the values of our natural frequencies, it's going to converge, it's going to get flat for frequency 1 before frequency 2 before frequency 3. And this is why sorting our natural frequencies after we find the eigenvalues is going to be really important, because we might be interested in the first 2, 3, 4, 5 natural frequencies and see how many elements does it take before the first 5, let's say, have converged. And we might not be too worried about the 6th, 7th, and higher after that, because typically those are going to add very little power to our full solution. So we kind of need to know up front what are the natural frequencies we are interested in obtaining good results for or reliable results for, and then see when do that many natural frequencies converge, and then we can say we've used enough elements. What we can't really do up front is arbitrarily say we're going to use 1,000 elements and we're going to assume that the first 5 natural frequencies are going to be good. In a very simple system, that's probably going to be the case. Probably it's going to be reliable for the first 5 natural frequencies if we use that many elements. However, every system is going to be different, and as they get more complicated, or as things approach being nonlinear, or we have sudden geometry changes maybe in our structure, it might take more and more elements for our natural frequencies to start converging. So that's why we need to really plot it with an increasing number of elements to see when do they flatten off? When have we used enough elements for however many natural frequencies we're interested in? So the convergence testing is typically time consuming because we do have to rerun it, and every time we rerun it, it's with more and more elements, so it actually takes longer each time we're rerunning it. But it allows us to trust a little bit more the natural frequencies that we start to get as we're adding more elements. So what is the problem of how many elements we're using? If we use too few, as we saw in the examples, too few elements means our solutions are definitely going to be inaccurate. We're going to get the first few natural frequencies, but they are going to be far away from what the true value is, very likely. However, and they're going to get further away as the frequencies get higher. The first natural frequency will be, as a percent difference, closer than the second to the actual, closer to the third than the actual. And the other problem with using too few elements is if we're interested in the first several natural frequencies, we won't be able to even see them if we use too few elements because we only get as many natural frequencies as we have degrees of freedom. And then the problem of using too many elements, well, as discussed at the beginning, this increases the computation time roughly quadratically in how long it takes to run the FEA. So if we jump right to using 1 million or 10 million elements, it might take forever to actually do that computation when what we're interested in, the first few natural frequencies, may have converged well before using that many elements. And the other problem could be when the elements become too small, the computer itself might start to make errors as it's going to make some rounding errors and truncation errors when the size of the elements become way too small. But the biggest thing with using too many elements is just how long it's going to take to run.